Off the Greek island of Antikythera, the sea gave up a group of corroded bronze fragments. At first, they did not look like the remains of an instrument. They looked like wreckage, green-stained metal, broken edges, layers of corrosion, and shapes too damaged to explain themselves. Then researchers began to see something inside the cracks. Teeth. Not the teeth of an animal, but the teeth of gears. Across the surviving fragments, at least 30 bronze gear wheels remain. The discovery did not immediately tell anyone what the object had done. It created a harder question. How could a cluster of broken metal from the ancient world contain a machine complex enough that its purpose had to be read back from fragments? The fragments came from a real archaeological site, a cargo shipwreck off Antikythera. Sponge divers found the wreck at the beginning of the 20th century. The recovery carried on through 1900 and 1901 with assistance from the Greek Royal Navy. The site produced statues, glassware, coins, and other cargo from the ancient Mediterranean world. The wreck itself is usually dated to roughly 60 to 50 BCE, but the mechanism appears to have been made earlier, toward the end of the 2nd century BCE. Those dates should not be collapsed into one story. The shipwreck tells us when the object entered the sea. It does not by itself tell us when the mechanism was designed, who made it, or why it was on board. It gives us the object's modern point of recovery. It does not give us its full biography. What survived is not a complete machine. It is a damaged collection of 82 fragments. Only about 1/3 of the original mechanism remains. Some gear teeth survive, some dial divisions survive, some inscriptions survive, but much of the original structure is gone. The missing parts matter. They include portions of the gear trains, parts of the original displays, and the physical relationships that once connected one section to another. So the task is not to uncover a finished answer hidden inside the corrosion. It is to test whether the fragments, the surviving marks, and the readable inscriptions can support a coherent explanation. Every claim about the mechanism has to begin with that condition. The object is evidence, the complete machine is not. For decades, the fragments could be studied only from their surfaces and from ordinary X-rays. That changed in 2005. High-resolution surface imaging made fine details of inscriptions easier to read. X-ray computed tomography allowed researchers to examine structures buried inside the corroded bronze. The scans revealed gear arrangements that could not be seen from the outside. They also exposed thousands of previously unread text characters. No single layer of evidence solved the mechanism. Gear teeth provided ratios, dial divisions provided cycles, inscriptions named or described parts of the celestial display. Imaging showed how some of those pieces occupied the same surviving fragments. Only when those layers were compared could researchers begin to separate what the object directly preserves from what a reconstruction must infer. The clearest answer appears on the back of the mechanism. There, surviving spiral dials and gear systems record recurring cycles of the moon and calendar. One large dial followed a 19-year Metonic cycle, 235 lunar months arranged across 5 turns of a spiral. Another followed the Saros cycle, 223 lunar months used to mark recurring eclipse possibilities. The eclipse dial did more than mark a simple warning. Its glyphs recorded whether an event was solar or lunar, gave a predicted time and associated the event with additional characteristics. This was not a modern astronomical forecast. Its calculations were periodic. and its accuracy had limits, but the mechanism clearly turned recurring observations into a physical system of ratios, pointers, inscriptions, and gears. A surviving gear arrangement also gave the lunar display a controlled unevenness, reflecting the changing apparent speed of the moon across the sky. And the same instrument linked celestial time to civic time. A subsidiary dial connected the broader calendar cycle to Panhellenic games, including Olympia. The moon, calendars, eclipse cycles, and the rhythm of public life were brought into one mechanical framework. The front of the mechanism is more difficult. It is also the part that has attracted the boldest reconstructions. X-ray imaging revealed inscriptions referring to the sun, the moon, and the 5 planets known in antiquity. Together with the surviving structure, those inscriptions point toward a front display of an ancient Greek cosmos. Researchers have proposed several ways that such a display could have been arranged. One widely discussed model attempts to make the planetary periods, the inscriptions, the surviving gear traces, and the limited interior space fit together in a single working mechanism. That is a serious scholarly reconstruction. It is not a surviving original. The overall direction of the front display has strong evidentiary support. The exact transmission system, full gear arrangement, and original layout do not. The lost front can therefore be studied. It cannot be presented as fully recovered. This difference is the center of the mystery. The rear calendar, lunar, and eclipse systems are more securely reconstructed because more direct structural evidence survives. The planetary display at the front rests on a narrower base. Inscriptions, partial traces, known cycles, and models designed to test whether those clues can work together. A reconstruction can be valuable precisely because it makes its assumptions visible. It can show one coherent way the evidence may fit. It cannot turn missing gears into recovered gears. The same boundary applies to the object's human history. The surviving evidence does not identify its maker, workshop, buyer, intended user, or exact purpose. It does not tell us why it traveled on that ship. And one surviving mechanism cannot establish how many comparable instruments once existed. Research has continued to revise readings and reconstruction details as the evidence is reassessed. That is not a failure to solve the object, it is the method working as it should. The Antikythera mechanism matters because the surviving fragments are already enough to show something concrete. More than 2,000 years ago, a maker or makers could encode astronomical cycles, calendrical systems, mathematical ratios, and skilled bronze work into a single mechanical instrument. Much of that instrument is gone. Its full front display remains partly reconstructed. Its maker and original context remain unknown. Its possible technical relatives have not survived for us to compare, but the evidence that remains is not small. It shows ancient knowledge being translated into gears, dials, inscriptions, and moving relationships. That is the real force of the mechanism. Not a complete answer and not an excuse to invent one. A damaged object, read carefully, can still reveal how precisely human beings once tried to make the order of the sky visible in bronze.